Motion under constant acceleration. Another word for this to use for constant acceleration is motion under uniform acceleration. This is when the velocity changes at a constant rate. If you look at the graphs to the right, this is a graphical model of this type of motion. The bottom graph shows acceleration versus time, and notice how the acceleration is staying constant. You have a horizontal line. The middle graph is velocity versus time. Notice it is a straight line with a positive slope in this case. It follows the linear relationship of y equals mx plus b. And if you look at position versus time, the top graph, notice there is a quadratic relationship there. There is a parabola. Should spend some time studying these graphs. This is what the graphs look like for motion under constant acceleration or uniform acceleration. If we look at just the velocity versus time graph, and we start at an initial velocity of v naught, or v sub 0, at time t equals 0. If the object is moving under constant acceleration, you can predict what its velocity will be at a later time, because its final velocity will always equal its initial velocity plus what's changing it. And what's changing it in this case is that it is accelerating at a constant rate over time. So if you apply what you have learned in algebra for a linear relationship, y equals mx plus b, the y-axis in this case represents the velocity, and the x-axis represents time. The slope is actually the acceleration, and v naught would be the y-intercept. So from y equals mx plus b, you could write the equation v, the final velocity, equals v naught, the initial velocity, plus the acceleration times the time. Acceleration times time equals the change in velocity. So if you look at the graph there, velocity change equals acceleration times time. The slope of that line there is the acceleration, and also the time interval is included. So you start at the initial velocity v, you accelerate over time, and you end up at the final velocity v at some later time t. Take a minute to look at that graph. If we want to find the average velocity between time t equals 0 and some other later time, if the acceleration is constant, the velocity versus time graph, you will have a linear relationship, and the average will turn out to be just adding up the initial and final velocities and dividing by 2. So if you look at the graph, right in the middle between v naught and v on the y-axis, the average is right in the center. So it's like finding an average between two test scores. You would add up the two test scores and divide by 2. But in this case, the two values represent the initial and final velocities. This is unique to the situation where the motion is under constant or uniform acceleration. If you have a graph like this, and you want to find the average velocity between the initial and final velocity, because it's not a linear relationship, in this case, the average will be less than 1/2 v naught plus v. And you could also have the case where the graph would look like this, where the average would be pulled up and be greater than v naught plus v. We're primarily going to look at the case where the graph is linear and the average will be the arithmetic average, 1/2 v naught plus v. So let's do a problem here. Let's say at time t equals 0, an object is at position x naught, its initial position, and has a velocity of v naught, its initial velocity. Let's say it moves with constant uniform acceleration. What is its position at any later time t? Well, let's write the relationship. You could start with the relationship for average velocity. It equals displacement over time, or change in x over change in t. You could solve this for change in x, the displacement. It would equal the average velocity times the time interval. if we let the time interval start at t equals 0, we could remove the triangle and just write t. And if the acceleration is constant, we have a relationship for v average now. If we expand out the displacement, which is x minus x naught, we could rewrite this equation as you see here, where we have x equals x naught plus v average times time. And then for v average, we could substitute our new relationship of 1/2 v naught plus v. We could do that. And continuing on with this idea, we also have a relationship for v final. We could substitute that relationship in. This v equals v naught plus at. So if we go about this algebraic process here, it starts to look rather complicated. But if we, after the substitution of v naught plus at in for v, if we distribute the 1/2, and we also distribute the t at the end within the parentheses, and add like terms, we'll finally arrive at this conclusion that the final position will equal the initial position plus what's changing it. And what's changing it is that it has velocity over time, this object, and it also has acceleration over time. But look at the velocity term. It's just the initial velocity times the time. And look at the acceleration term. It's 1/2 the acceleration times the time squared. It's quadratic in time. So if we look at a graph of this, if you look at the horizontal line on the bottom, that's when the position doesn't change. Then you have a straight line, a linear relationship, where the position changes because you have some initial velocity over time. And then the curved line, the parabola over there, the position is also changing because you have some acceleration acting over time. And you get that quadratic relationship. So position as a function of time is quadratic. And we call this equation, this x equals x naught plus v naught t plus 1/2 at squared, position as a function of time, we call it the world line. Let's look at it in more detail. So if you look at the object's position, that's what x is. Its position at some point in time. You'll start at an initial position. You will be displaced due to your initial velocity over time. And you'll also be displaced due to the velocity resulting from this acceleration. You're speeding up. So these three terms will help you determine what your final position will be. You have to know what your initial position is. You'll have to know what your initial velocity is. And you'll have to know what your acceleration is. And we're assuming this acceleration is constant or uniform. And then if you know what the time interval is, you'll be able to predict what your final position is due to these changes. Take a minute to look at this graph. So let's do another problem here. Let's say you're making an emergency landing, and the airport has a runway that's only 90 meters long. Let's say the plane touches down at 80 meters per second right at the beginning of the runway, then decelerates at a constant rate of 4 meters per second squared. So it'll be constant or uniform acceleration. Will it stop before the end of the runway? Well, let's see if we can figure this out. Well, we'll take time t equals 0 to be the instant of touchdown. We'll let x equal 0 at that starting point. So we say x naught will equal 0. We'll take the positive direction to be the end of the runway. So the original direction of motion will make positive. So our initial velocity will be positive, or 80 meters per second, and our acceleration or deceleration will be negative because it's opposing the motion. It's slowing the plane down. and that's 4 meters per second squared. So we're just writing down what's given and we're putting it in physics terms, and we're defining a coordinate system, which way is positive, which way is negative. All the motion is considered along a straight line. One direction is positive, the other direction is negative. So here's what we got. Our initial position is 0, our initial velocity is 80 meters per second, and our acceleration is negative 4 meters per second squared. The question is how long will it take for this thing to stop? That is, when will V final equal 0 meters per second? So if you start with that equation we talked about in class, V equals V naught plus AT, if you set that to 0 and you solve for the time, you'll get negative V naught over A. That'll give you the time interval, or how long it will take to stop. So let's do the numbers on that. We have 80 meters per second for V naught and negative 4 meters per second squared for acceleration. This formula here predicts it'll take 20 seconds to stop. So from V equals V naught plus AT, you could use that to solve for the time it takes to stop. Okay, next question, how far will it get in this time? Now we'll use our world line, because that's position as a function of time. The final position equals the initial position, plus the initial velocity times the time, plus 1/2 the acceleration times the time squared. So if we do the numbers, we start at an initial position of 0. Our initial velocity was 80 meters per second for 20 seconds, plus 1/2 negative 4 meters per second squared, our acceleration, and the time was 20 seconds again, but we have to square it. So if you do the numbers here, it comes out to be 800 meters. So will we be able to stop in time? If you look at the original problem, it said we had a runway of 900 meters, so we should be able to stop in time. So it should be safe. We have a little fudge factor there. So the equations of motion for uniform acceleration, they can, be overwhelming at first, but you really only need to know 5 of them. You should know what displacement stands for. It's the final position minus the initial position, or x minus x naught. You can also write the displacement is equal to the average velocity times the time. And what's unique about this formula, if the acceleration is constant, there's a neat way to find the average velocity. We simply use 1/2 the final velocity plus the initial velocity, or you could think of it as the initial velocity plus the final velocity divided by 2. It's like it's like taking the average of 2 test scores. We also could just write it like this: change in x, or displacement, equals 1/2 V naught plus V times the time. And then there's this equation that came from that linear relationship of the graph of velocity versus time. We had the final velocity equals the initial velocity plus the acceleration times the time, or V equals V naught plus AT. And then we had the world line equation here. The final position equals the initial position plus the initial velocity times the time plus 1/2 the acceleration times the time squared. That's a key equation. And there's also this one we will derive, most likely in class, which has the square of the final velocity is equal to the initial velocity squared plus 2 times the acceleration times the displacement. That's a very useful formula. It's time independent, and it's one of the what we've been calling in class the Fab Five. Now it's good to write these equations down on a 3x5 card and just have them to work with when you're working out problems.